Thanks very much for those of you who stuck around to the end. I want to talk today about something that's a little bit different. Well, I want to talk about maybe the same thing, but from a different perspective, that is. And that's the geometric measure theory point of view. On the Gaussian isoperimetric inequality. And okay, so maybe I want to start by giving a definition, which I claim is, in some sense, the right definition of Gaussian surface area. I'll call it Gaussian perimeter because that's what they call it in this community. So I gave a definition on the first day involving you sort of blow up your set a little bit, you take the Gaussian measure of the blow up and you sort of take the infinitesimal growth of that, right? As you blow up by a very small amount. And I think that definition makes a lot of intuitive sense, but when I show you this new definition and its properties, I hope you'll agree that it's somehow a better one. Okay, whatever that means. So I'm going to make this definition using the usual, so I'm not going to start with the definition, I'll come up with the definition at the end. Using the usual analysis trick of starting with a definition that makes sense for smooth objects, and then doing some sort of duality and ending up with a definition that makes sense for arbitrary objects. Okay, so let me start with, let's suppose that A is as nice as possible. So I have a subset of Rn. Let's say that it's open, bounded, and C infinity boundary. Okay. So in particular, the fact that it's bounded means that the boundary is going to be compact, and so and C infinity, and so I will have no trouble taking whatever regularity I need. Everything converges, all derivatives exist, and so on. Okay, so now for this set, I hope you'll agree that a decent definition for the perimeter, the Gaussian perimeter, is I integrate on the boundary of the set the Gaussian density with respect to the n-1 dimensional surface area measure, which I like to write like this. Okay. So that's something that I think is a good definition of Gaussian surface area for smooth sets. And of course, it coincides, as I claimed, I didn't prove it, with the Minkowski content that I defined in the first lecture. Okay. So now I want to start sort of fiddling around with this. And the first thing that I'm going to do, so I always end up with the Zoom windows blocking what I need. Okay. So let me define nu, a map from the boundary to Rn, the outward unit normal. All right, and then with that definition, I can do this sort of silly thing, I guess, of putting here the norm of the outward unit normal, which is of course always 1. Okay, but of course, the Euclidean norm of a vector can also be written in its dual form as the sup over all W having Euclidean norm 1, or at most 1, let's say, of nu inner product W. And then I'm going to pull the sup outside the integral, and instead of having at every point a sup, I'm going to take a sup over vector fields, right? A sup over vectors that depend on the point. Okay, so I have the sup of the integral on the boundary of my vector field, of my outer unit normal, let's say, inner product, some vector field against the Gaussian density on the boundary of the set. And here, I'm going to take the sup over all vector fields so let's say C compactly supported smooth functions from Rn to Rn with the property that pointwise they are bounded by 1 in norm, right? So let's see, okay, just to maybe be extra sure. So in this last equality that I wrote, so the inequality is trivial, right? Because, sorry, the other inequality is trivial, right? Because at every point, this thing is a vector with norm at most 1. Okay, the inequality so that was trivial. And for the inequality in this direction, it's maybe not quite as trivial because on the right-hand side, you have an extra smoothness condition, right, which you didn't have on the line above. Right, the line above you really get to take the supremum at every point, and now I'm asking for a smooth vector field. But for this direction, you can take, to get equality, you just take psi to be an extension of the normal vector field. And because of the smoothness assumptions that I made at the beginning, I can take a smooth extension of the normal vector field. This is, I guess, using Whitney's extension theorem, which also has norm bounded by 1. And it also is compactly supported because my boundary is compact. Okay, so it's inequality. Okay. So now I'm going to write, oh yeah, and I want to make one more extra definition, which is that I'm going to call curly X the set of all vector fields that are admissible in this supremum. So the set of all CC infinity vector fields, which are pointwise bounded, which have norm pointwise bounded by 1. Okay. And now, so let me rewrite this. Integral on the boundary. I'm going to, of course, it doesn't make any difference if I put d gamma dx inside the inner product like that, because it's just a scalar. And this is the supremum over all psi in x. Okay, so I haven't really done anything in that line. But now the point is the following. So what I'm doing is I'm integrating on the boundary of set the outward normal times the vector inner product with a vector field, right? So the outward flux of some vector field. And by the Gauss-Green, Stokes, whatever you want to call it, theorem, this is the same thing as the integral on the set of the divergence of the vector field. Dx. Okay. And now, okay, this one I should already get, okay, I'm just going to maybe manipulate it just a little bit, maybe to put it in a form that I think looks a little bit nicer. Integral on the set. I'm going to use the product rule for the divergence here. So I get the divergence of psi, and then I get psi inner product, the divergence of the gradient of, psi inner product, the gradient of the density of the Gaussian density, and the gradient of the Gaussian density is just minus x times the Gaussian density. So I get a minus psi inner product x. And then everything was multiplied by the Gaussian density dx, so I can just write d gamma. Okay. Right. So now at this point, I'm very happy. And I'm very happy because what I've written in the last line makes sense for any measurable set A. Right? For any measurable set A, for any smooth vector field, this integral exists. Right? Now the supremum, if my set A is a nasty set, the supremum could well be infinite, but that's fine. I'm happy to have sets that have infinite Gaussian surface area. Okay, so this is going to be now my definition. For any measurable set A, the Gaussian perimeter of that set is defined by what I just wrote above. The supremum over all smooth vector fields compactly supported of the divergence, the integral on the set of the divergence minus the inner product with the position d gamma of x. And it's the supremum over smooth compactly supported vector fields with norm bounded by 1. Okay. So that's the definition of Gaussian perimeter. If you're familiar with the notion of the definition of functions of bounded variation, it's really the exact same argument here. Let me put that in parentheses. That this you can also see as the sort of bounded variation norm of the indicator function Okay. But if that doesn't mean anything to you, then don't worry. Okay. Now, I promised to you that this is somehow, I think, the right definition, and I don't expect that to be maybe clear why. So let me maybe write down some nice properties. I'll leave them as exercises. Most of them are not so hard. This definition satisfies the following properties. So the first one, which is, I think, very clear, is that if I have two sets which differ on a set of measure 0, then they have the same perimeter. Okay. The second one is a sort of limiting version of this. So if I have a bunch of sets which are converging in measure to another set, so converging in the sense that the measure of the symmetric difference goes to 0, then okay, it's okay. Let me write something maybe. Okay, you shouldn't expect that the perimeters converge to the perimeter, right? The reason you shouldn't expect that the perimeters converge to the perimeter is because, for example, I could have an be this set with an extremely wiggly boundary, right? And then as n gets larger, the boundary is still sort of the same width, but getting more wiggly. No, sorry. It's not the same width. It's getting narrower and more wiggly, but it's getting wiggly faster than it's getting narrower. And so the perimeters could be blowing up, but it could still converge in the sense that I wrote above to the set that just has a flat boundary. Okay, so the perimeters don't converge to the perimeter, but you do have an inequality. So the lim inf as n goes to infinity of the perimeters is larger than the perimeter of the limit. Okay. The next thing that happens is a sort of a converse. Okay, so in general, you have sets converging. Their perimeters could be, the limiting perimeters could be larger than the perimeter of the limit, but you can always find a sequence where you get equality. So let's see, for every A, there exists a sequence of sets approaching A, which are very nice. Bounded, open, C infinity boundary, satisfying that they converge. Whoa, seems I closed my window. Apologize for that. Don't know what happened. I think maybe my program crashed. Oh, it says I can restore. Ah, excellent. It even saved had an autosave. That's great. Now I just have to share it again. Okay. Ah, sorry, and I noticed while my program was crashed that there was a question in the chat, but I seem to have not. Oh, let's see. If you had positive reach, it would converge. Are you asking? Is that you're asking about number 2 there, Galina?
Yes.
I think if you're asking about number 2, then the answer is yes. Yeah, basically the only reason it doesn't converge is because of what I just showed you.
So you could, in principle, for more nice sets, you could define it not as a supremum over all vector fields, but an extension of the normal vector field if it existed.
Yes, exactly. Because you really expect, I mean, for nice sets, the supremum is attained by the normal vector field. Extended. Right. Okay, let's see. If I close, what window am I selecting? This one. So if I close that, then I'm still okay. All right, where was it? Here. Okay, I only lost about half a second of writing. Okay, so there exist bounded open sets. Oops. Okay, bounded open C infinity boundary sets whose measures, I mean, which converge to my target set in the sense that the measure of the symmetric difference goes to 0, and the perimeter of these guys converges to the perimeter of the other one. Okay, so not every sequence, I mean, when you have a general sequence converging, the perimeters do not converge, but you can always approach any set with a sequence of converging very nice sets whose perimeters converge. And these two last properties that I wrote here put together, I like to sort of summarize by saying that the perimeter, the Gaussian perimeter that I defined, it's the lower semi-continuous extension of the smooth version of Gaussian perimeter. So that is to say, when you talk about a Gaussian perimeter, I hope, when your sets are smooth, it's obvious what the definition should be. All the definitions that you could come up with are equivalent. Now, when you have sort of slightly nasty sets, there are various definitions that you could have. Okay, the definition that I've written down here, the Gaussian perimeter, the soup over all things of the divergence, etc., is the lower semi-continuous extension from the class of smooth sets to the class of all sets. Okay, so this is particularly nice because it means, for example, that it will be smaller. It will be smaller than most other extensions, right? Because it's lower semi-continuous. Okay, it also tells you this. So this part 2 and part 3 tell you that there is another. I mean, it would be equivalent to define the perimeter of an arbitrary measurable set as the inf over all approximating sequences of smooth sets of their perimeter. Okay. So let's see. Another one is that another property is that the Gaussian perimeter of any set is the Gaussian perimeter of its complement. Okay, and then just one last piece to sort of tie this into what I had before is that the 4 properties that I wrote are all false for the Gaussian-Minkowski content that I defined in the first lecture. Okay, so this is what I mean by the Gaussian perimeter is sort of the right definition of Gaussian surface area. Okay, in the sense that when your sets are strange, it still has all the really nice properties that you would like, whereas the other definitions do not. Okay. Now, I want to, like I said, tell you about the it's a little smaller so I can see my clock. Okay. The geometric measure theory point of view on this. And so the basic outline, I mean, the way that they look at these things is you want to prove an isoperimetric inequality. You want to prove that a certain set minimizes the Gaussian perimeter. So the way that you do it is you first have to show that minimizers exist, and then you sort of do calculus on them, right? Like in the same way that in calculus, if you know that you minimize a function, then and you know there is a minimizer of a function, then like it's the gradient is 0 and the second derivative is the Hessian is positive semi-definite and so on, right? So I want to do the same sort of thing here. I'm going to first prove that there are minimizers, and then I'm going to take those minimizers and study perturbations of them. And by studying perturbations, I will learn a lot about what they do. So I have to deal with the first one first. And the issue is, well, okay, I'll write it as a theorem. It's not completely trivial to prove, and I will not prove it. But the fact is that for any bound, the family of sets or of indicator functions of sets with Gaussian perimeter bounded is compact. Let's say okay, I think of this as a subset of L1 functions. Okay, so it's a compact set of functions. So I'm not going to prove it, like I said, but let me just sort of say 2 words about it. The first one is that closed is easy. It follows from the lower semi-continuity of the perimeter. Okay, and totally bounded is more difficult. And I should have said this at the beginning, but I'll tell you a reference. So basically what you show that you can do is you can, right, I have to show that for every epsilon, I can epsilon approximate every function in this class with some finite collection of functions. And the finite collection of functions that you can take, for example, is I take a grid of side length epsilon, and it's in Rn. It doesn't cover the whole of Rn. It just has like 1 over epsilon, total width, right? So I'm covering most of Rn with very small boxes. And you look at functions which are sort of measurable with respect to this grid, meaning they're, every square is either completely filled in or completely not filled in. Right, sets of this form. Okay, now for every epsilon, there are a finite number of sets of this form, right? And you can show that they well approximate everything in this class. Right? The main issue being that in order to do that, you have to basically get estimates using the definition of perimeter of the number of boxes which are sort of not very well covered. Okay, so, and yes, so there's a reference. In fact, all of the stuff that I'm telling you about geometric measure theory, the reference that I use is the book by Francesco Maggi. And the title is long and I always forget it, but it starts with sets of finite perimeter. Okay. Now everything in this book is for Rn, just because the geometric measure theory community, I mean, is for the Lebesgue measure, just because that's what these guys like to do, but it's not very much work to adapt it for Gaussian measures. Okay, now.
Joe?
Yes.
Yeah, just a quick question. So I think my intuition is getting confused. Like, why can't you have something like extremely wiggly, but that's very far out? And then, like, if you make it wiggly enough, can't you make it have arbitrary large perimeter? In Gaussian
So sorry, you're talking about
let's
this
say in
theorem?
2D. Yeah. The
Sure.
fact that it's totally bounded, I just get confused.
So if it's too wiggly, then you won't have perimeter bounded by C.
Yeah, but I
mean,
put it really, really far out and make it very, very wiggly until I hit C. And then, like, how am I going to hit it with these?
It's sure. So it's those examples are actually sort of working in my favor as far as this argument goes, because if the wiggling is way out here, outside of the grid, which has side length epsilon, 1 over epsilon, right? Then the measure. Okay, maybe let me say it like this.
Daniel, I think Daniel is asking if the set A should be bounded, but it's not. It's an L1, right?
No. No, it's not,
because it's the indicator of the set. I see. So like,
yes.
Right. It's just, I mean, the amount of the set that's outside of this box is tiny. Yeah. Okay. It's not, you're not.
That's right. As epsilon goes to 0, then in measure, it's nothing.
Yes. Okay, that makes perfect sense. Okay. Yeah.
Yes. Totally bounded with respect to the L1 thing. So yeah. Okay. Cool. All right. Now, let's see. So this tells me that minimizers exist, I claim. So let me write that. Corollary. Let's see. Okay, Gaussian perimeter minimizers exist. Okay, what I mean by that is, for every V in the interval 0, 1, there exists a subset of Rn with Gaussian measure V minimizing Gaussian perimeter. So for all B with measure B, they have smaller perimeter. I mean, bigger perimeter. Right? Sorry, you can't read that, but hopefully you know what it says anyway. Okay. There are sets which have minimal Gaussian perimeter with respect to any Gaussian measure. Okay, and the proof is, even without knowing that minimizers exist, you let AN all having measure V be a minimizing sequence. Okay, without loss of generality, I can assume that I've already passed to an appropriate subsequence so that there's a limit, right? Because the theorem tells me that this sequence belongs to a compact set, right? And so it has a converging subsequence. And then according to the exercise that I wrote before, the perimeter of A is smaller than the lim inf of the perimeters of AN. Okay, but this was, but also because these measures are converging, the measures of the differences are converging to 0, I have the measure of A is equal to V. Okay, and so then because it's smaller than the lim inf for the perimeters as a minimizing sequence, then it must be minimal. Okay, so compactness plus lower semi-continuity tells you that you have minimizers. All right, so now that you have minimizers, okay, you want to study them, you want to figure out, what properties must these minimizers have, and then hopefully in the end you conclude that the minimizers must actually be half spaces. That's the Gaussian isoperimetric inequality. Now, it turns out that this is not completely an easy task. Okay. So the first thing you have to do is some sort of slightly difficult stuff that was studied in great detail in the second half of the 20th century, which is the regularity theory of the minimizers of this thing. So now, for the rest of today, just to avoid as many technical details as I can, I'm going to take the planar case. Okay, everything now will be in R2, which is good enough because we showed on the first day that once you prove the Gaussian isoperimetric inequality in R2, then it follows. Okay. Now, okay, in R, yes.
Yeah, just one more silly question. Like for the first part about the fact that the set is closed, like do you need like some sort of Blaschke or some sort of selection principle? Oh no, because it's arbitrary sets. Okay. Sorry. Or it's arbitrary functions, arbitrary sets.
So, okay, so let's see. So I'm going to be working in R2, just because it will make things a little bit easier to state. And okay, so if I have a minimizer, and from now on, whenever I write a minimizer, I mean a minimizer of the Gaussian perimeter with respect to the volume constraint, with respect to the constraint on the measure, then, okay. I would like to say that A is a nice set with a smooth boundary. I can't quite do that because of this this property that I told you that the perimeter doesn't care about sets of measure 0, right? And so you can definitely have a perimeter minimizer, which is a strange set in the sense that it was a nice set, but then someone messed it up by adding a set of measure 0. So I have to deal with that here. So if I have a perimeter minimizer, then there exists some A tilde, okay, such that A tilde is open. It's equal to A except for a set of measure 0. And the topological boundary of A tilde is an embedded C infinity curve in the plane. Okay. When I say embedded C infinity curve, it could have like multiple connected components in principle, but it's embedded in the sense that none of those connected components actually come close to touching each other. All right. So maybe I'll just say it and not write it. One reason that I do this in R2 instead of in higher dimensions is this is not quite true in higher dimensions. When you have dimensions 8 and above, then you're allowed to have a singular set, which has codimension at least 8. But when we're doing it in the plane, then these things don't pop up. Okay. So now that I know minimizers exist and I know that they're regular, then you can start to do some calculus on them. So I'm just going to sort of briefly outline the sort of things that you can do. So from now on, I'm going to say, let A be a minimizer. And I'm going to assume that I have done the regularity theory already, and that I have removed already the set of measure 0 that I needed in order to make it open and have a nice C infinity boundary. Okay. So now what you're going to do is I want to study perturbations of the set. And the way that I'm going to make perturbations of the set is I am going to take a vector field just to avoid all possible technical issues. I'm going to make it a C infinity vector field, compactly supported. It's on R2. Okay, and when I have a nice vector field like this, I can flow along it. So take F, the flow for time t along the vector field x is going to be a nice function from R2 to R2, satisfying that the time derivatives of the flow are given by the vector field. Okay, and this thing exists, and it's C infinity diffeomorphism by the sort of ODE, the usual ODE stuff. So this is called flow along x. Something causes my window to close all the time. Must be hitting it with my hand or something. It's a good thing that this thing has auto saves. All right. Okay, so I have my vector field. And let me introduce maybe a little bit more notation. So I already had my nu, which was the outer unit normal. I'm also going to let tau be the unit tangent, or a unit tangent. I choose to fix an orientation in advance, and I just take this unit tangent, and kappa will be the curvature, which is the derivative in the direction of the unit tangent of the unit normal, inner product the unit tangent. And hopefully I have the sign right here, but let me draw a picture. So I have my set A on this side. So the normal points out. The tangent, it doesn't matter which direction it points in. Right? So this is the normal, this is the tangent to the boundary. And the derivative of the normal in the tangent direction here has a positive inner product with the tangent. So this is positive curvature. That's what I want. Yes. Okay. And if the boundary looks like this, then here it will have negative curvature. Okay. So positive curvature means bulging outwards. Okay. Now, right. So what's going on here is I have my set A. Let me draw another one. And I'm perturbing it by choosing a compactly supported vector field. Like, for example, this little sort of bump. So this vector field is supposed to be like a bump function in the direction of the outer unit normal. And then what I'm going to do is I'm going to take my flow and I'm going to flow my set. And when I flow my set, I'm going to end up with a sort of slightly perturbed set like that, right? As I flow it for positive time along the vector field. Okay. So I'm going to define ATX to be the flow along the vector field x of the set A in direction for time t. All right. So now the whole point of this is now I'm defining some sort of smooth perturbations of my set. I can differentiate things in t, and I can do calculus. Okay, and let's see. I am not going to have time to prove these formulas, but let me write them anyway. Yes. So
like F0 is just the identity? Is that?
Yes, you're right. ODEs need an initial condition, right?
Okay.
This is I would mark down my undergraduates if they didn't do that. Yes. Okay. Yes, it's the vector field starting at time 0 as the identity function. Yeah, so that's why it's when t is 0. Yeah, so let me write that also. I start from A, and then I run t positive or negative. Negative is fine too. And I get a smooth perturbation, a one parameter family of perturbations in my set. Okay, now you can do some formulas, some calculus. Let me write one piece of notation just so the formulas look a little bit nicer. When I write gamma 1 like that, what I mean is so gamma 1 is like I use it when I'm integrating along curves. It's the length element, right? So length element, or if you prefer, one-dimensional Hausdorff measure. Okay, it's a length element along the curve weighted with respect to the Gaussian measure. Okay. Now, okay, so let me write down two formulas. If I take the measure of my set and I differentiate it, then at time 0, what I get is, so what's the first order change to the measure of my set? And let me put the x there to emphasize that I'm making this change with respect to the vector field, capital X. And what I get is the normal component of X integrated along the boundary with respect to the Gaussian measure. And I think that without doing the calculation, this is kind of an obvious formula, right? Because I have my set. Here's my set A. I have my vector field X, which is pushing me sort of in the normal direction, right? And how much measure do I gain? Well, I gain the strength of the push multiplied by the Gaussian measure around where I'm pushing, right?
Sorry.
And of course, you know, if my, yes.
At the beginning of the lemma, we are missing 1D, or we have 1 dt too much?
Yes, thank you. Like that. The derivative, yeah, the first order change in the measure of the set at time 0. Yes. Is that better now? I think so.
Yeah, clear, thanks.
Okay. I should make more mistakes more often because it's much better when people say something and I don't have to just talk to myself. Okay, so this is the first formula. This is the change in measure. Now the second formula is I want to know what's the change, the infinitesimal change at time 0 of the perimeter. And this one is a little bit harder to see if you're not already familiar with this this kind of business. And I was thinking of maybe proving it, but I think I don't have time. But it's in the notes, which will be uploaded after the talk. It's also somehow proportional to how much I'm pushing in the normal direction, but there is an extra factor here, which is the curvature at the point minus x inner product, x being the point that I'm at, x inner product the normal the unit normal. Okay. So again, it's proportional to how hard I'm pushing, but there is this extra factor. So you know what else? Just sort of write very vaguely is this comes from the geometry of the curve, and this comes from the Gaussian measure. In the sense that if you were to do this calculation without the Gaussian measure and just do like the Lebesgue length of the curve, then you wouldn't have the second term. Okay. And to explain the term that comes from the geometry, I mean, I don't know how to explain that it's really the curvature exactly, but clearly if I'm pushing like this.
Joe, I'm so sorry. Could I ask that
Yes.
you mean mean curvature or Gauss curvature?
I'm in R2.
Okay.
So there's only one curvature.
Only one curve. Okay, good.
Yeah. But yes, if I was in Rn, it would be mean curvature. Yes. Well, okay. You have to be careful about mean curvature because people normalize it differently. If I was in Rn, it would be the trace of the second fundamental form.
Which is mean curvature, right?
Yeah, but some people divide by the dimension.
Oh,
it's mean
okay.
curvature, right? Yeah. Okay. So when curvature is positive and you're pushing in the positive direction, the boundary gets bigger, right? Whereas when curvature is negative and you're pushing outwards, then the boundary gets shorter, right? So just to sort of give some intuition as to why you get a curvature term popping up here. Now, I'm not going to show this calculation, but I'll tell you the consequence, which is not so hard. That if you have a perimeter minimizer, then the quantity kappa minus x times the normal is constant on the boundary. Okay. So we have this thing, which is like it's sort of curvature. It's like some sort of modified curvature. Okay, and it's constant on the boundary of any minimal set, right? And the reason is, and I'll leave the sort of the real argument out of it, but this is basically the reason. So if not, there exists a vector field x such that the first order change in the measure along this vector field is 0, but the first order change in perimeter along this vector field is negative. Okay, and by sort of modifying this a little bit and doing some sort of implicit function theorem stuff, you can show that there actually exists a set with exactly the same measure as your original set, but a smaller perimeter, and so then you're not minimal. Okay, this is basically like Lagrange multipliers in this calculus of variation setting. All right, so okay, I don't know how familiar this is with everyone, but when you do isoperimetric problems with respect to the Lebesgue measure, you get something very similar, except that you only have the curvature. Okay, and now when you're in R2 and you only have the curvature, then everything is very nice because there are only a few sets which have a boundary with constant curvature, right? There's straight lines which have constant curvature 0, and there's circles, right, which have constant curvature 1 over the radius. Okay, and that's it. So at this point, if you're doing the Euclidean isoperimetric problem, then you're done, right? Because all of the sets which satisfy this criterion here, okay, are either have infinite measure because the boundaries are just straight lines, right? Or there's circles, which are the isoperimetric sets. Okay. Now the unfortunate thing for Gaussian is that we're not done. So there are a number of sets or a bunch of them, like really lots, having constant this thing, curvature minus inner product x and the normal. Okay, here are some examples. So the first example that makes us happy because it's the ones that actually minimize the Gaussian isoperimetric problem are sets of the form, okay, well, let me write sets of the form the set of all points x where x inner product a is, let's have it be smaller than or equal to b. And just for normalization, I can say that a is a unit normal, right? Because when I make a unit normal, a unit vector like this, it is the outward unit normal, right? So then if I have a set of this form, then my outward unit normal is always a, curvature always 0, and the outward unit normal inner product of position is equal to b on the boundary, right? So so this formula here is constant on the boundary, so that should make us happy because these are the minimizers. Okay, but you have some others. So one example is origin-centered balls. Right? An origin-centered ball has outward unit normal being equal to the normalized position. It has curvature being equal to 1 over the radius. And it has, therefore, this inner product between the normal and the position is the radius. Okay, and so this thing here is radius plus 1 over radius. Oh, I guess radius minus, there's a minus here, 1 over radius minus radius, okay, which is constant on the boundary, right? Okay. Now, balls which are not centered at the origin do not have this thing being constant, right? Because they have constant curvature, but the inner product between the normal and the position is not constant. So for balls to be potential minimizers, they have to be origin centered. Now, there is another family of weirder sets, which were constructed in some reference that I have, that I've given in the notes. The point is that, you know, if I set this thing to be equal to some fixed constant, lambda, let's say, then it defines an ODE. It's like a second order ODE, or a system of ODEs, okay? So what you can do is you can start this equation anywhere you like, and you take the tangent to be whatever you like, and you can solve it, and you get a curve. Now, most of the time, you get these sort of nice looking curves, which are not the boundaries of nice sets. So they're sort of, you get curves that look like this, or you get curves that look like this. Okay, but if you choose your parameters carefully, you will get curves which are closed, simple closed curves. So in particular, you can get curves which look like this. You can get curves which look sort of like rounded triangles. And in fact, you can get curves which look like rounded n-gons for any n. I don't know, maybe I can dare to try and draw a rounded hexagon. Okay, that's a terrible rounded hexagon. I shouldn't have. Okay. But you can generate a whole bunch of these things which are not half spaces, but which have the right thing being constant on the boundary. So I won't really have time to say much about this, but you need to pass to second derivatives, right? Because like in calculus, you know, if you have a function that you're trying to minimize and it has multiple critical points, then you need to check which of those critical points has a positive semi-definite Hessian, and only those could be the minimizers. And there's a theorem, which now that you know, I mean, once you know the formula for the second derivative, which probably won't bother writing down, it's not that hard to show. And this was shown by McGonigal and Ross in about 15-ish, I think, that only half spaces have, I'll put it in quotes, a non-negative Hessian. Okay, in the right sense. So this is sort of, okay, so once you know this, it proves the isoperimetric inequality using these tools. It also actually tells you a little bit more, which is maybe nice, which is it tells you that in some sense, half spaces are the only local minimizers of perimeter, because I'm not sure if it has any applications in probability, but you know, maybe it's nice for some other things. Okay, and with that, I thank you for your attention. There's more details with formulas for second derivatives and so on in the notes that will be online shortly.